Guys, welcome to the second lesson of the chapter. So last lesson we talked about confidence intervals for the mean for generally for large samples and generally when sigma is known. So now we're looking at confidence intervals for the mean, assuming that we don't know the population standard deviation, and generally for small samples. So first thing we want to do is be able to determine the confidence interval for the mean, assuming these conditions with small sample size and so on. So we're going to go and get started. So again, we're going to kind of recap. Remember that we used a z-distribution, assuming that we knew the population standard deviation. Okay, so we used assuming that we know the standard deviation, and generally for large sample sizes. Again, the sample size has to be, greater than or equal to 30. That's considered a large sample size. There are times when this is not the case. In these cases, we need to use what we call the student t-distribution or the t-distribution. So when do you use one versus the other? All right. So these are kind of summarizing the characteristics that you need. So the sample, regardless of which one you choose, the sample always has to be a random sample. So it has to be, selected randomly. If the sigma is known, then if the sample size is large, meaning greater than or equal to 30, then go ahead and use the z-distribution. If the sample size is small, well, you can still use the z-distribution if the population is normally distributed. If the sample size is large, but sigma is unknown, then go ahead and use a z-distribution. Even though we don't know the sigma, if the sample size is large enough, then you can go ahead and use the z. If the sample size is small, though, then you would use the t-distribution, assuming that the population is normally distributed. So keep in mind the population has to be normally distributed if the sample size is small and you don't know the sigma. Now, generally we like to use a z-distribution for large samples. If you don't know sigma, then this is where you use S to approximate it. So in this case, you would use the sample standard deviation, S, instead. All right. So what is this t-distribution? How does it look like? So that's what we want to go over next. Okay. So what are the characteristics and how does it look like? So the characteristics of the t-distribution. The t-distribution looks remarkably like the z-distribution or the standard bell curve. So it is bell-shaped. It is symmetric about the mean. A lot of the characteristics they share, the mean, median, and mode are equal to 0 and located at the center. The curve never touches the x-axis. However, there are some ways that it differs. All right. So for the t-distribution, the spread is different. So the variance or standard deviation is greater than 1. The t-distribution consists of a bunch of curves that change in shape depending on what we call degrees of freedom. We'll talk about that in a little bit. And then as the sample size increases, the t-distribution approaches the standard bell curve. So as you can see in this example, if you have a really, really small sample size, like 5 or something, then it's not gonna really look like the bell curve. It's still gonna be bell shaped, but it's gonna be really spread out if you can tell. As you approach 30, then this distribution gets smaller. The variance gets closer to 1, because right now the variance is greater than 1. But as you increase the sample size, that variance starts approaching 1, and it starts looking like the z-distribution, the bell curve. All right, an important concept to realize is that as you increase the sample size, this is why we use a z-distribution, because the t approaches z. All right. So the t-distribution uses what we call degrees of freedom. Degrees of freedom are basically numbers that are free to vary after a sample statistic has been computed. So, so for example, and these numbers are important. The reason why we use these numbers is because the degrees of freedom tell you which t-curve to use. All right, so because the t-curve, like we said, is a family of curves, and they tell you which one to use because depending on the scenario. All right, because these t-curves are remarkably different from each other. So you want to make sure you use the right one for your calculation. So they tell the researcher which t-curve to use. So this should say which. So that was just a typo there. So they tell them which t-curve to use when a t-distribution consists of a family of curves. So for example, if the mean of 5 values is 10, then 4 of the values we say are free to change. So they're free to vary. But once you select 4 values, then the 5th value must be a specific number to get a mean of 10. So like for example, if you had, I don't know, let's just make up some numbers. So 1, 2, 3, 4. And let's say you wanted a mean of, let's say you wanted a mean of like 2 or something, right? Well, in order to get a mean of 2, in this case, these numbers can change, right? They can be any number that we want, but once we choose those values, this number is fixed. Okay, so if I add these numbers, 1 plus 2 plus 3 plus 4, well, 4 plus 3 is 7, 7 plus 2 is 9, 9 plus 1 is 10, right? So this is equal to 10. But I need to figure out, so this number has to be a specific number so that I can get a mean of 5. Well, how many, or of 2, I'm sorry, I said 2 earlier. Let's say I want a mean of 2. All right, well, we know that we're dividing by 5 because we have 5 numbers here. So then what number does this have to be to get 2? Well, this has to be a specific number, right? The only way that we can get 2 from this is if x were equal to, if x were equal to 0, right? So if x were equal to 0, then this will give me 2, because 10 divided by 5 is 2. So we say that we have 4 degrees of freedom. These guys are free to change, but this guy cannot. Cannot change. So once these change, this guy has to be a certain value. All right. So in this case, we have 4 degrees of freedom. These guys can change and vary. Okay. So we have 4 degrees of freedom in that example. All right, and then the curve on the bottom actually shows you another example of the t-distribution. So as the degrees of freedom change, right, as the degrees of freedom get larger, then it starts approaching the z curve. All right, but as the sample size decreases, or that means the degrees of freedom decrease, and then it starts diverging from the z curve. So it starts looking different. All right. So the formula for the degrees of freedom is real simple. It's just taking the sample size minus 1, so n minus 1. And this is the formula. So this formula looks very similar to the one that we did for when the mean is known, right? When the standard deviation is known. Okay. So it was in this example, it's going to be x bar plus or minus t alpha over 2 times s over square root of n. Okay, so that's another way of writing it. So remember that in the other lesson, this was a z-score, but now it is a t-score. All right. So to find in the formula, notice that you need to find the critical values given by the t. To find the critical values of t, you need to use the z-distribution table. So I'm going to give you an example of how that's used. All right. So let's say we wanted to find the t value, the critical value for the t, for a 95% confidence interval, assuming that the sample size is 22. Again, the sample size is 22, which is less than 30. So that means we can go ahead and use the t. So the degrees of freedom is, in this case, is 21 because we're going to take the sample size minus 1. So then what you're going to do is you're going to go to the t table, and you're going to look up 95% confidence interval, and then you're going to look up for the degrees of freedom on the left side and trace them down until you get your t-score. Real simple. This actually tells you what you need to do. This actually tells you what the t-score is. There's no need to calculate it, though, in the same way that we did for the z-curve. So this is a good thing. Easier for you guys to be able to reference. All right, so your t-score is 2.080. All right, so let's look at an example of how this works. So in the first example, we have a random sample of 10 children found that their average growth for the first year was 9.8 inches. Assume the variable is normally distributed and the sample standard deviation is 0.96 inches. Find the 95% confidence interval of the population mean for growth during the first year. So we got a sample size of 10, which is less than the 30. So note that we have a small sample size. And then, so it was 9.8 inches. So they said that their average growth was 9.8 inches. So we have the x bar is 9.8. That's the sample mean. The sample average is 9.8 inches. Assume the variable is normally distributed and the sample standard deviation is 0.96. So we know the sample standard deviation, but we don't know sigma, right? So in this case, sigma is unknown. So it's unknown in this example. So definitely a t-distribution problem. Find the 95% confidence interval of the population mean for growth. So we need to find out what the t alpha over 2 is. Here, let me erase that. So we need to find out what the t alpha over 2 is equal to. So this is where we reference the table. All right, so we want a 90%. So we have a sample size of 10, and we have a 95% confidence interval. And when we do the z-table, we ignore the one tail. We're only interested in the two tails, okay? So for 95%, two tails, that means and then for a degree of freedom, we need to find our degree of freedom. So our degree of freedom is simply given by n minus 1, which is 10 minus 1, which is 9. So 9 degrees of freedom. Looks like over here. And 95% is over here. All right. So that is your t-score. So that's our critical value, 2.262. All right. So now we can go ahead and do the calculation for the 95% confidence interval. T alpha over 2 s over square root of n. So 9.8 plus or minus 2.262, just plug and chug. and the sample size is 10. All right, so you go ahead and plug in those numbers. Remember, you're going to get an interval because you're going to do the plus or minus version of it. Okay, let me go ahead and I'm going to do that on the calculator here. All right, so I'm going to do in chunks here, 0.96. Okay. So for the big number, I got 10.49. We'll round it to 2 decimals. For the small number, I got 9.11. All right, and that's our confidence interval. So this is saying that if we continually did samples of 10 children and then constructed the confidence intervals, that 90% of the confidence, 95% of the confidence intervals will contain the population mean. Okay, so there's a 95% chance, that this contains the population mean. All right. So the last example, the data represents a random sample of the number of home fires started by candles for the past several years. Find the 99% confidence interval for the mean number of home fires started by candles each year. So we're going to, just quickly calculate the average of this data set. So add them up. And then divide by, so we got 7 fires, 7 pieces of data here, 2, 4, 6, 7. So then we have 7,041.4. All right, so that is going to be our X bar. All right, and then our N is 7, which is less than the 30. And our sigma is unknown, right? We don't know our sigma. But we can estimate the S. So since we don't know sigma, we need to estimate S then. We need to figure out what the standard deviation is. So we're going to do that on the calculator and plug it in, and then I'll let you know what I get for the answer. All right, so I went ahead and plug the standard deviation, plug the data on the calculator. I got 1610.3. All right, so large standard deviation. So now we got all the data we need except for the T alpha over 2. So we got, we need our degree of freedom. So if our sample size is 7, our degree of freedom is 6, 7 minus 1. So now we're going to look up degrees of freedom of 6, and we want a 99% confidence interval. So 99% and 6. All right, so we need to go to 99%. Let me zoom out a little bit. And we want degrees of freedom of 6. So that's 3.707. Right there. All right, 3.707. Okay, so then now we can go ahead and plug into the formula. So we got X bar plus or minus T alpha over 2 times S over square root of N. All right, and then we're going to get our answer, and we're going to put it in interval format. Okay, I'm going to go ahead and calculate that real quick. So 3.707 times 7 square rooted. So 9,297.6. Okay. And 4,785.19. All right, and that's our confidence interval for the problem. So we're 99% confident that this interval contains the population mean. That the population mean is between those two numbers. All right, and that's the interpretation of the interval. All right, guys, I hope this found this useful. It's pretty straightforward for the most part. Just use the same formula to find the confidence interval. Sometimes they give you the data. Sometimes you have to, sometimes they give you the numbers. But either way, you have to determine whether you're going to use a z or the t, depending on the scenario, and then go from there. All right, guys, good luck.